What's going on, everybody? This is going to be Mr. Diamond working out, and actually two example problems for doing Keq calculations. Instead of just doing the actual expressions, we're going to work out problems where you need to actually do a calculation from them and get an answer. We've got two problems here. I'm going to read them both, and if you want to pause the video and attempt these by yourself, you're welcome to do so. You will be getting a worksheet tomorrow that will probably be due, I don't know, Monday, Tuesday. We'll see exactly when I make it due. Probably one of those 2 days, though. It's just got a couple of example problems for this that you'll turn in, but these are for practice. So our first example problem up here is calculate the Keq for the reversible reaction of carbon dioxide and hydrogen forming carbon monoxide and water. Assume all are gases, the reaction takes place in a 2-liter container, and there are 0.1908 moles of CO2, 0.0908 moles of H2, 0.0092 moles of CO2, and 0.0092 moles of H2O. And then it also asks which side of the reaction is favored. And that's going to call back to something in your notes, so you may need to go back and double check that just in case. And then question number 2, for this given reaction, determine the unknown concentrations. So our reaction is 2A that is aqueous plus 3B that is aqueous plus C that is a solid reversibly reacts to form A2B, which is aqueous, plus B2C, which is a solid. And then it gives you some concentrations over here. B is our unknown that we're going to try to solve for. Concentration of A is 0.825 molar, of C is 1.00 molar. Of A2B is 1.65 molar, and of B2C is 6.25 molar, and then it also tells you that the Keq is 2.5. Now, I also have a little note here. All of these values are completely made up. I could not find an example that fit all the criteria I wanted for a second example, so I ended up having to make one up, and so this answer might be horribly weird, and I don't know yet because I haven't solved these yet because I'm going to solve them with you. So don't freak out if this answer is weird or if it seems like something's really off. That totally could happen. That could be because of, the way I made the problem. So go ahead, and if you want to attempt it, I would pause the video here and start working out these problems. And if you're not, I guess just wait a second and I'll be back. All right, welcome back. For our first example, the first thing we need, and the first thing you need for pretty much all of these problems, is you need to make sure you have a balanced equation. So if you don't have a balanced equation, you're going to need to make one. In this case, we've got a reversible reaction, and we've got all of our pieces, and it says they're all gases. So carbon dioxide is CO2, and that's a gas. We got to leave gaps because we may need to go back and balance this, so make sure you remember that. Plus hydrogen, which hydrogen is diatomic, so it's H2, gas. You could also check down here if you forgot that. Are going to react to form. Now I almost messed up there, and I mean I did mess up, but we're gonna fix it and salvage it a little bit. We need to make sure we do a double-headed arrow. It seems minor, but I won't be as picky about it in my class, but in some of your other classes, especially if you take advanced chemistry classes later on in your life, having the wrong arrow will mean you just get the problem wrong. You will miss points for that. So make sure that you're using a double-headed arrow for this. And it forms carbon monoxide gas, which is CO. Carbon is 1, and then mono is 1. Oxide is oxygen. And then water. So we've got H2O. It's a gas. Now, before we move on, let's make sure this is balanced. I'm going to zoom in a little bit now that you guys have kind of been able to read the whole question. So we've got one C and one C. We've got two O's. We've got two O's. We've got two H's. We've got two H's. So this one's convenient. It actually worked out to be just put ones on everything. That's kind of nice. Okay. Next step is we need to figure out what our expression is. So our expression is going to be, remember, we put our products on the top, our reactants on the bottom, and remember we ignore certain things. We ignore things that are not within the same phase. Specifically, that's usually going to be liquids and solids. Now, in this case, they're all gases, though, so we don't actually have to ignore anything. So our expression is going to be, again, products go on top. So we're going to put CO's concentration. I don't know if I mentioned it specifically in the notes, but just as a reminder, these brackets mean molar concentrations. So anytime you see these brackets like down here, this is telling you bracket M is molar concentration of, or bracket A is molar concentration of A, and that is 0.825. So bracket CO means we need the molar concentration of carbon monoxide. That's going to go to the first power. In fact, all of these are going to go to the first power because there is no coefficient other than 1. So I'm not going to bring that up on this one. And then we'll have H2O. That's our gas over here. And then all of that will be divided by our concentration of CO2 times our concentration of H2. Now, the only other thing that makes this problem tricky, because it seems like it's not going to be that bad. Some of you might have noticed that I was a jerk. I just realized my sound is a little bit loud, so I'm going to turn that down. I hope that wasn't blowing out any of your eardrums. Some of you might have noticed that I'm a little bit of a jerk here. Remember, brackets, like I just said, are molar concentration, and molar concentration are moles over liters. And I gave you moles and I gave you liters, but I did not give you molarity. So you actually are going to have to do some math and solve for each one of these. Now, you could step-by-step solve for each one, but what I'm going to do, because I'm really lazy and I don't want to have to rewrite multiple things and I don't want to have to do a bunch of different steps for it, I'm literally just going to plug them into those brackets. So for first one, I've got bracket. This is where my CO is. I've got 0.0092 moles, and then it's inside of a container that has 2 liters. Now you might go, well, if the container is 2 liters, how do we know that it is occupying 2 liters of space? Remember, it's a gas, so gases are going to expand to fill up their containers. So we can go ahead and just assume, well, those moles have to be evenly or somewhat evenly distributed inside of those 2 liters. Okay, next we're going to take our H2O. Our H2O is also 0.0092 moles inside of a 2-liter container. And again, you could work these out individually and then plug them in, but I'm really lazy. I'm just going to plug this all in my calculator in one go pretty much. Okay, our CO2 is 0.1908. That's moles inside of 2 liters. And finally, our H2 is 0.0908 moles inside of 2 liters. And there we have it. So now we can go ahead and plug this in. So what I'm going to do is I'm going to do some annoying parentheses to make it work out. I'm going to do double parenthesis, 0.0092 divided by 2, close parenthesis, and then times, you don't have to do times technically, but I assume most of you would want to do that, 0.0092 divided by 2, close parenthesis, close second parenthesis. So that's my entire top portion. Then divide by, I'm going to need 2 parentheses again, 0.1908 divided by 2. And then times, again, you don't need that times there, but 0.0908 divided by 2, close. I guess you don't actually need those either. All right, so we get an answer of 0.0048855272. Looking back at all of our sig figs, though, our lowest sig figs, now this one has 4, this one has 3, but these both only have 2. So we're actually going to round it to 2 sig figs. So 0.0049 is equal to our KEQ. And then if you look back in your notes, a KEQ that is less than 1, specifically if it's the further lower than 1 it is, the more it is going to be, or the greater it is 1 if it's the opposite. But that didn't make a ton of sense, and I feel like some of you might have gotten confused there. That was one of those ramble things that I sometimes do in class, but that I don't end up, that I think makes more sense in person. So going back to the notes, KEQ of greater than 1 means products are favored. KEQ of less than 1 means reactants are favored. In this case, this is less than 1, and I would say it's not like a ton less than 1. So I would just say that reactants are favored. And this means that if you do this reaction, if you were to start with equal amounts of all of these things in a reaction at the beginning, you will probably end up with more CO2 and H2. These guys are going to be more commonly formed. This reaction is more, you could think of it as stable, it takes less energy, it's a position that's more comfortable for all of the atoms involved. There's a bunch of different ways you could approach it. Now, if this number would have been like 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000you're probably barely going to get any of these things. And the opposite would be true if it would have been a really big number. If it would have been like 1,000,000, that would mean that the products are heavily favored. You don't have to get specific, but you might sometimes see reactants are favored, reactants are slightly favored, or reactants are strongly favored. If this would have been like 0.5, that's pretty close to 1, so that would have been reactants are slightly favored. That's just kind of to give you a little bit of an introduction to like some stuff that you might see later on when you're looking at this. I just realized there's like a reflection you can kind of see in my calculator up there. You can see the pencil. It's pretty cool. Okay, so our example, or our answer for this one is our KEQ is 0.0049, and our reactants are favored. Okay, going to our second example. For this given reaction to determine the unknown concentration, we have our reaction. Let's go ahead and write our KEQ expression. And again, remember as we go through this that this is all completely made up, so if something just doesn't seem to make sense, there's a good chance that it's just because it doesn't make sense. So products go on the top. But remember, like I mentioned in the last one, we get to ignore some things. Even though I gave you concentrations for every piece over here, I gave you a concentration for all 5 of them. Notice that this one is a solid, and this one is also a solid. And because both of those are solids, we don't actually count them in our equilibrium concentration. When they form solids, their concentration kind of becomes static. It becomes an intensive property that no longer is affected by the fact that it's in solution. So we are going to ignore them. My cat has decided she wants love. I don't know if you can hear that. It's gonna. You okay, Ellie? She's living her best life. She's been sleeping mostly. Okay. Let me pause this and love her for a moment. All right, I believe I have satisfied her for now. Don't worry, I didn't make you sit here awkwardly while I, just pet my cat. But we can ignore these 2 solid pieces. So for our KEQ expression, the only thing on the right side of the reaction that we care about is our A2B. And it doesn't have a coefficient out front, so it's got a 1 there, but normally we don't need to write it. I'm only going to write it this time because I want us to make sure that we remember we need to include those for the other sides. So on the other side, we've got 2a, so that means that we need to do a squared, because this coefficient is going to become the superscript, and it's aqueous. Then we're going to have our b that is cubed. As aqueous, so we count that. But our C we do not count because it is a solid. Okay. And then we know our KEQ already. We know our KEQ is going to be 2.5. And then we can just now fill in all of our information. I know some of you may not like it when I write it this way here. I'll do a little dividing line here. So this is our problem we're going to set up. This is us actually going to plug in the pieces. So our A2B is going to be 1.65. Our A squared is going to be 0.825 molar. That's squared. And then our unknown is going to be our B that is cubed here. So let's rearrange and get all of our pieces on one side. So we're going to multiply each side by our B cubed. And we're going to end up dividing by 2.5. And that will give us, once we do a cube root, and if you're like, Diamond, are you really going to make us plug a cube root into your calculator? Yes, I am. But I'll show you kind of the easy way to do it if you're not quite sure. So we'll get 1.65 over 0.825 squared. And then on the bottom, we've also got 2.5. And then this whole thing is cube rooted because we have to get rid of this cube. We only care about the concentration of B. So our concentration of B, let's start plugging it in. Okay, so we're going to get my calculator back on. 1.65. Okay, I guess I didn't need parentheses there, but just in case. Then I'm going to do the bottom. I'm going to do 0.825 squared, close parentheses off, times 2.5, close that second parentheses, and that should give me a number. Okay, and now this number, to do it to the cube root, sometimes there's a, you can go to your, special functions, you can find, there's, right here is a cube root, so you could do this. And that will give you your answer. But what you could also do, and I believe it should give you the same answer. So this is 9696969697. We're going to take that to the 1/3 power. And I believe, if you notice, that is the exact same number there. So if you don't want to, or your calculator doesn't have an ability to go and find this cube root function, you can just take something to the 1 over whatever root you're trying to find power. So if I was a huge jerk and made you do a fourth root question, you could do to the 1/4 power, and it would be the same as doing a fourth root. So that means our concentration of B is approximately 0.9897952063. But obviously, sig figs, looking at all of our questions, the KEQ is only got the 2 sig figs. So just to be safe, we're going to only go to 2 sig figs for our answer. And so our answer would be 0.99. And remember, this is a molarity. So our concentration of B is 0.99 molar, which actually does make sense. I'm pretty proud of myself. I was really worried this answer was going to come out with something really dumb and really big or really, really tiny. Okay, so that is how you do a KEQ expression. I hope that makes sense for you guys. I think Ellie ran away. Otherwise, I was going to let you guys see some Ellie camera time, but I think she left after she got her love, so I apologize for that. But you will get the worksheet tomorrow, which should be Thursday, and then you'll have Friday and Monday at least to work on it. I think Tuesday maybe when it's going to be due. That sounds good to me. We'll make it Tuesday. And then also on Tuesday, I will give you the next section of notes, which is going to be like this, but it's going to make it a little more complex, as I'm sure you're used to at this point. So I hope that makes sense to you guys. I hope you have a good rest of your day, and I hope you have a good rest of your week. And I hope to see/hear from you soon.